Look at this mechanical assembly line. It represents the first era of large language models, stateless text generators and chatbots, stamping out rigid, one-way answers. When we tried to make them do actual work, we entered the second era, rigid, code-driven workflows. Developers used static, directed acyclic graphs to force the model down predetermined paths, limiting what the AI could accomplish. This diagram compares that rigid flowchart on the left with where we are today on the right. We have entered the third era, autonomous, model-driven loops that interact directly with their environment to solve problems dynamically. But giving an AI agency immediately exposes three universal failure modes: runaway loops burning through tokens, monolithic context windows causing amnesia, and unsafe permission roulette. A better prompt cannot give an LLM a local file system or a way to bypass its own hardware memory limits. If the surrounding system is not designed to catch a runaway loop or enforce shell permissions, no amount of instruction tuning will make the agent reliable. These are not bugs in the model. They are the structural limits of working with a naked API. Anthropic's Claude Code is a terminal-native CLI agent designed to address these limits. It functions as a super agent, a system where the model does not just answer questions, but controls the environment around it. To understand exactly why it outperforms agents with hundreds of custom integrations, we have to look past the user interface and rebuild its underlying architecture, starting from a basic API call. The central engineering problem is taking a raw text predictor, which has no memory and no hands, and turning it into a stateful entity capable of executing complex, multi-step tasks without breaking down. The solution is an architecture known as the harness. It is a local, strictly defined runtime environment wrapped around the AI. By separating the dumb local body, the harness, from the smart brain, the large language model, developers can engineer away those universal failure modes at a structural level. This node is the LLM brain, driving the TAOR loop: think, act, observe, repeat. A cyclical track surrounds it. The runtime is 50 lines of code executing continuously. Without hard-coded paths, the model evaluates its progress and triggers a stop signal when done. A loop needs tools to be useful. The instinct for most developers is to build specialized API wrappers, like writing a custom Jira integration for every potential task. That approach creates brittle systems that constantly break. The harness opts for capability primitives instead: read, write, execute, and connect. Execute acts as a universal adapter, piping standard bash directly into the model. Instead of rigid wrappers, the agent has the exact same command line access a human engineer uses. By combining a self-directed loop with these four highly composable primitive tools, the agent can navigate an infinite number of workflows, outscaling rigid integration architectures. That infinite potential immediately hits the architecture's strictest bottleneck, the hard token limit of the LLM context window. This gauge illustrates context collapse. If you force an agent to conduct heavy research and write code in the same session, junk data quickly fills the window, degrading memory and triggering hallucinations until the system fractures. To protect the primary intelligence, the architecture introduces context isolation through the use of subagents. When heavy tasks arise, the main agent delegates downward. The subagent runs an isolated loop inside its own token budget, churning raw data without threatening the parent's capacity. Once complete, it condenses findings into a summary, passes it up, and clears its memory. The architecture treats context as a scarce economy. Monolithic memory is fragile, so subagents act as expendable, isolated workers to keep the core intelligence sharp. Subagents solve context limits through sequential delegation, but enterprise workflows require true parallel execution. This diagram introduces agent teams. These are not parent and child processes. They are entirely independent, peer processes running simultaneously alongside each other. They coordinate their efforts through inter-process communication and a shared file system. The system relies on a self-claiming task model. As soon as one agent finishes writing authentication logic and goes idle, it immediately pulls the next unblocked item, like testing or documentation, directly from the shared list. This peer structure enables specialized tasks, like deploying long-running garbage collection agents. While foreground agents actively build new features, a background agent continuously scans the older codebase, cleaning up technical debt in real time. Agent teams bypass the single-threaded limitation native to LLMs. They allow an organization to apply concurrent implementation at scale, with multiple models working on the same codebase at the same time. Handing a self-directed loop direct access to your terminal and file system introduces an extreme security risk. To secure the environment, we introduce a rigid gate between the agent's loop and external tools. This observability and guardrail layer is built on deterministic lifecycle hooks. Before execution, a pre-tool use hook intercepts the request to audit the intention or statically block dangerous actions. Similarly, post-tool use hooks enforce strict quality control after the fact, such as triggering a linter the exact moment the agent saves a file. These hooks execute zero AI logic. Where the LLM is probabilistic and prone to hallucination, the hooks reintroduce absolute mathematical determinism to the system. For further validation, the Model Context Protocol, or MCP, acts as a universal bridge. It allows the agent to safely query live structured logs and inspect runtime states to verify that the code it just wrote actually works. The probabilistic reasoning of a language model is powerful but dangerous on its own. By surrounding it with deterministic guardrails, developers neutralize permission roulette entirely. Look at the complete diagram we've built. We have the central LLM brain operating inside the TAOR loop, equipped with primitive tools, isolated by subagents, running in parallel teams, and secured by deterministic hooks. This entire outer structure, the body, is model agnostic. You can swap the LLM at the center without rebuilding the tools, the memory layers, or the permissions. That separation introduces our final architectural takeaway: the principle of coevolution and shrinking scaffolding. Foundational models naturally improve in reasoning and context retention over time. As the brain gets smarter, the hard-coded architectural scaffolding surrounding it should deliberately be deleted. Watch this time-lapse of massive steel scaffolding being dismantled to reveal a self-supporting structure. If your orchestration code becomes more complex with every new model release, you are building in the wrong direction and fighting the model's natural trajectory. Systems architects must design AI applications differently. We are no longer building rigid workflows. We are building modular, shrinking harnesses designed to protect and